morning, everyone. Welcome to the session on applications. I'm Devi Parekh from Georgia Tech and Facebook AI Research.
Hi, everybody. I'm Georgia. I'm from Facebook AI Research, and welcome. So it's my pleasure to introduce the first talk. It's titled, you can come up. It's titled Photometric Stereo and Participating Media Considering Shape-Dependent Forward Scatter. And the presenter is Yuki Fujimura. Excellent.
Thank you for the person. I'm Yuki Fujimura of Kyoto University in Japan. I start my presentation. Our goal is to reconstruct the 3D shape of objects in participating media. Please see the image on the left of this slide. This image was captured in diluted milk, and in participating media, a captured image is degraded by scattered light. So it is difficult to use traditional 3D reconstruction techniques. By using our method, we can reconstruct the 3D shape from degraded images. First of all, I'll explain the light scattering in participating media. In participating media, light is scattered by suspended particles. So we observe 4 components at the camera. The first one is a direct component. The direct component is directly reflected on the surface and reaches the camera. Besides the direct component, we have 3 scattering components. The first one is a backscatter component shown by blue line. The backscatter component reaches the camera without arriving at the surface due to backscatter. And the second one is a surface camera forward scatter. In this figure, we observe a surface point P, and the reflected light from another point is also observed at the camera via forward scatter between the camera and the surface. And the last one is the source surface forward scatter component, shown by an orange line. This component reaches the surface after forward scatter from a light source. In this study, we model these 4 components and we reconstruct the 3D shape. This is the overview of our method. It is important to know that scattered light depends on the shape of object. So we propose an iterative algorithm. First, we remove backscatter using a previous method. Then we initialize the shape, and we compute the surface camera forward scatter and remove it. After that, we use photometric stereo, considering source surface forward scatter to reconstruct the surface normals. After that, we update the shape and repeat these steps to refine the shape. In this presentation, I'd like to talk about 2 things. The first one is how to compute the scattering components. And the second one is how to remove scattering components. For the rest of this presentation, I explain these 2 points. And first, I'll begin with how to compute scattering components. First, I take a backscatter as an example. In this figure, we observe the surface point P, and in participating media, besides the direct component, we observe a scattering component due to a backscatter between the camera and the surface. So this scattering component is the sum of scattered light on the line of sight. So this component can be computed using integral between the surface and the camera. However, this integral cannot be computed in a closed form. To address this problem, we use an analytical form using a lookup table. In a previous study, analytical form using a lookup table has been proposed, and in this equation, FUV is a lookup table. Its indices are U and V. That is, by computing the integral of FUV numerically in advance, we can compute the scattering components efficiently. Next, I explain a surface camera force scatter. In this figure, when we observe surface point P, the scattered light from point Q is observed. And this relation can be written by a linear equation. KPQ is the effect of surface camera force scatter, and it also can be computed using a lookup table. And then we consider all discrete points observed at the camera, and we derive this linear system, where L and LS are n-dimensional vectors, and K is n by n matrix, and n is the number of pixels. Next, I'd like to move on to the next point, how to remove scattering components. As I said, surface camera force scatter is written by a linear system. So theoretically, it can be solved using the inverse matrix. A previous method approximates thing as a plane under orthogonal projection, and this made K a special invariant point spectral function. So in this case, this linear system can be solved efficiently using a first Coulomb transform. On the other hand, we consider specially variant kernels because of the shape-dependent force scatter. So it is difficult to solve the linear system directly. So to address this problem, we approximate the matrix K as a sparse matrix. We assume the effect of the force scatter from a distant point is small, so we approximate K as the effect from a near point and a constant term. This K hat is a sparse matrix because it depends on the near points. By using this approximation, we derive this sparse linear system, and we can remove the force scatter to solve this sparse linear system. Now we demonstrate our experiment. First, we show the experiment with synthesized data. We synthesized the images from a 3D sphere model. And this is the result. The first row shows the output normals, and the second row shows the angular error map, and the third row shows the reconstructed shape. In this experiment, we initialize the shape of the plane, and we show the each output of the iteration. As you can see, we observe the improvement and the convergence of the iteration. Next, we show the experiment with real data. This is our experimental environment. We use a 60 centimeter cubic tank, and we put a target object and pour diluted milk as a participating medium. This is the result of a sphere. The first row shows the output normals, and the second row shows the angular error map, and the third row shows the reconstructed shape. In this experiment, we compare our method and the backscatter-only method. In highly turbulent media, the backscatter-only method fails due to a strong force scatter. On the other hand, our method can improve the 3D reconstruction. This is another result. We use a shell as a target object. And in this experiment, we change the concentration of our participating medium. As you can see, in highly turbulent media, the backscatter-only method cannot reconstruct the 3D shape accurately. On the other hand, our method can reconstruct the local details of the shell. Conclusion. We have proposed a photometric stereo in participating media. Our method models a shape-dependent force scatter. To compute the force scatter, we use analytical form using a lookup table. The sparse matrix approximation enables its removal. Experiment with synthesized and real data demonstrates that our method can improve 3D reconstruction in participating media. Thank you for your attention.
Thank you very much. Any questions from the audience? Okay, I don't see one, so I'm going to ask you one. Have you thought of any applications where your work might be useful for? In our experiment, we experiment our method underwater scene, but our method is applicable, can be applicable to the other thing like fog or smoke or something. Okay, thank you very much. Let's thank the speaker again.
Our next speaker is Xiaowei Hu, and he's going to tell us about direction-aware spatial context features for shadow detection.
Thanks for the introduction. Hello, everyone. I'm Xiaowei Hu from the Chinese University of Hong Kong. It's my pleasure to be here to present our work, Direction-Aware Spatial Context Features for shadow detection. This is a joint work with Lei Zhu, Professor Fu, Professor Qin, and Professor Heng. Shadow detection is a fundamental problem in computer vision. We aim to generate binary masks to indicate the shadow region for the input images. Knowing where the shadow is helps to get the light condition, camera parameters, the shape and position of objects. However, the presence of shadow could degrade the performance of object detection and tracking. Shadow detection has been widely studied in the past years. We compare particularly with the last two works. Very recently, SCGN and stacked CNN apply the data-driven approaches by learning features using deep neural networks. However, they may still misrecognize the black objects as shadows and miss some unobvious shadows. Look at this image. We may think the left person is a killer, since he is holding a knife that points at the right person. But when we look at the global image, we can see a totally different story. The killer is the right person instead. When we understand the shadow, we have the same situation. Just like in this example, if we look at the local region in the image, it's hard to decide whether it's a black object or a shadow. We need to look at a larger region to know whether this is a shadow or not. So we argue that shadow detection requires an understanding of the global image context. More than that, we want to argue the global image context can be further analyzed in a direction-aware manner. Look at this image. When we compare region A and region B, we can see that region B gives a strong indication that A is a shadow. But when we look at the region A and region C, it's hard to tell whether A is a shadow from the image context in region C. Look at this example. The shadow is located on the background with different colors. If we use the traditional methods, the shadow on the yellow region may be lost. But if we can consider the image context in a direction-aware manner, we can propagate the shadow information from the left and the bottom. We can also use the information from the left and the right to infer the shadow on the yellow region. Then, our method can more effectively detect the shadow in such region. In order to propagate the global image context, we adopt the spatial recurrent neural network, which generates the spatial context features. Given an input feature map, we use an independent data translation to aggregate local spatial context for each of the 4 directions. Here, taking the red direction as an example, the feature value is updated by its left neighbor. This process is repeated from the left to the right on the whole feature map. The weight is shared and learned automatically, like the traditional recurrent neural network. By fusing the results from the 4 directions, each pixel knows the spatial context along the 4 directions. By having 2 rounds of data translations, each pixel can get the global spatial context for learning features. In details, taking a 2D feature map from a convolutional neural network as the input, we first perform a 1-by-1 convolution, followed by recurrent translation in 4 directions. We fuse the result into an intermediate feature map. Then, the whole process is repeated to generate the overall spatial context feature. In order to get the direction-aware spatial context, we adopt the attention mechanism to generate a set of weights. We split them into 4 maps of attention weights and times them with the spatial context features along different directions in an element-wise manner. These weights are shared in the 2 rounds of spatial RNN. Hence, we can get the DSC features by selectively using the spatial context features along different directions. This process is named as the Direction-Aware Spatial Context Module, DSC module for short. Then, we adopt multiple DSC modules in a deep neural network. Given an input image, we extract features with different resolutions over the convolutional neural network layers and apply a DSC module to generate DSC features for each layer. Then, we combine the convolutional features with the DSC features together and upsample them to the size of input image. The upsampled feature maps are combined into the multi-level integrated features. And we predict a score map at each layer by a deep supervision mechanism. Finally, we fuse all the score maps to produce the shadow detection result of the network. We train our model on the SBU training set and test it on other 2 datasets. We use the weighted cross-entropy loss to optimize our network. The loss is the summation of L1 and L2. L1 helps balance the detection of shadows and non-shadows. L2 helps the network focus on learning the class that is difficult to be classified. Please see our paper for the details. In testing, we use the mean of the score maps over the MLIF layer and the fusion layer as the final shadow detection result. Like a number of other works, we apply CRF as a post-processing to refine the shadow boundary. Here we show the results. We compare our method with the most recent shadow detection methods, SCGN and stacked CNN. We can see that our method outperforms the others for both benchmark datasets by a large margin. Here are the visual comparison results. Input image, ground truth, our results. The results of other methods. We can see that our method can recognize the black object as non-shadow. And our method can effectively detect the shadows across the background of different colors, but others may fail. Here is another comparison. We perform an experiment to evaluate the network design. The basic is a network built by removing all the DSC modules from the overall network. Basic plus context considers spatial context, but ignores the direction-aware attention weights. We can see that considering the DSC features can lead to obvious improvement. And here are the visual comparison results. However, our method may fail in a case with many small shadows, a case with a large black region, and a case with soft shadows. Furthermore, we can adopt our network for shadow removal by predicting the shadow-free images, and also achieve the best performance on these 2 shadow removal datasets. You may find the results in this archive paper. In conclusion, we present the direction-aware spatial context features for shadow detection and removal. We also achieve the state-of-the-art performance on 2 benchmark datasets for shadow detection and another 2 benchmark datasets for shadow removal. Our code and the results have been released at the website. Welcome to see us in the poster section. That's for the talk. Thank you very much.
Are there any questions for the speaker? There are microphones at both ends of the room, so feel free to walk up to those. No, maybe I can start with one. So you mentioned how your error rate has dropped significantly relative to the state of the art.
Yeah.
So can you comment a little bit on what the remaining challenges are? Are there do you need more sophisticated models, or do you think you need just more data? I saw that you only have a few thousand images in your data set.
Yes, I think for the shadow detection or the shadow removal, we need to understand the shadow region, which requires to compare the shadow region with the surrounding regions. So that's why we argue that the context information is very important. For the training set, it's true for that for the deep learning models, more training sets leads to a better performance. So since we just have a limited training set, maybe we need to develop the models to achieve a better result. But if we can have more data, I think the performance will be better. Thank you.
Thank you. And our last presentation in the oral session is going to be by Yan Li, and he's going to present discriminative learning of latent features for zero-shot recognition.
Well, hi everyone. I will give a talk about discriminative learning of latent features for zero-shot recognition. And my talk can be divided into 4 parts. Firstly, I will talk about some background for zero-shot learning. Well, zero-shot learning problem is a classification problem, but the difference between zero-shot learning and the standard classification problem is that the training set and the test set will have a disjoint label space in zero-shot learning. Well, that is to say, test classes in zero-shot learning are unseen classes. How is it possible? How is it possible if we have never seen the training images of panda? How to recognize it? To recognize unseen classes, zero-shot learning relies on some extra semantic information such as attributes. For example, if I tell you the giant panda has black and white fur, and the panda has a body shape typical of bears, maybe you can recognize it. Thus, we have 2 spaces in zero-shot learning: a vector space and a vector space and a semantic space. And with the help of semantic information, we could classify unseen categories without any training images. Then I will introduce the typical zero-shot learning approaches. And the basic idea is to learn a mapping function from the vector space to the semantic space. During training, our goal is to learn such a function from seen classes, and then we directly apply the learned function to project the images of unseen classes to the same semantic space. And finally, we could use nearest neighbor classification to perform the prediction. The key challenge in such a problem, the key challenge in such approach is the domain shift problem. The mapping function learned from seen classes will not generalize well on unseen classes. To solve this issue, previous zero-shot learning works. This means the manner in which the general shared representations are utilized in both the visual and semantic spaces. And for visual space, image features are typically treated by using pre-trained scene models, aiming to obtain general image representations for the semantic space. The human designed attributes are defined as semantic representations. The attributes are usually shared in many categories, and it is desired for knowledge transfer between categories. Thus, in typical zero-shot learning approaches, the image features and the semantic representations are fixed and predefined. The main focus of previous works is to learn the proper mapping function. Although such approach has achieved promising results, we believe that it is still necessary to retrospect zero-shot learning from another viewpoint. We notice that the final goal of zero-shot learning is to classify unseen categories. Thus, the visual features and the semantic representations should be discriminative to recognize such different categories. Then we review previous works to see whether the utilized visual and semantic representations are discriminative nodes. We can see that for visual space, the features learned from a pre-trained scene model are actually restricted to a fixed set, and it is not optimal for a particular zero-shot learning task. And for the semantic space, if there exist two categories sharing too many attributes, they will be hardly distinguishable. So there exist two solutions for zero-shot learning. To solve the domain shift problem, the general shared features are required. On the other hand, to classify different classes, the learned discriminative features are needed. And we try to solve zero-shot learning task with learned discriminative features, and it is a new viewpoint for zero-shot learning. Then we'll briefly introduce our method. The main contribution of our method is that in both visual and semantic spaces, we propose an end-to-end model to learn latent discriminative features. This is the framework of our method. In the visual space, we propose a cascaded zoom-in mechanism to learn features from object-centric regions, while in the semantic space, we aim to jointly learn the user-defined attributes and the latent discriminative attributes. And the learning of latent attributes is formulated as a category ranking problem to ensure their discriminativeness. And we first introduce the proposed incrementally zooming approach, which consists two steps. First, our model could produce the locations of the attentional region and then crop the region with a mask. Then we use bilinear interpolation to zoom the cropped region to the same size with the original image. Well, in the semantic space, we introduce an augmented attribute space where an image is projected into both user-defined attributes and latent discriminative attributes. The user-defined attributes are fixed and usually shared between categories, while the latent discriminative attributes are learned with the triplet laws, with regulating the interclass and intraclass distances. Finally, our model is evaluated on two standard zero-shot learning data sets. We can see that on both these sides, our model achieves the state-of-the-art results. And we also show the discovered regions by the proposed zoom night. And generally, our model progressively searches for final regions until it finds the main objects. Well, thanks for listening.
Thank you. Any questions from the audience? Okay, no. Okay, I can ask you a question.
Yes.
I was wondering if you have done any quantitative analysis that shows how important it is to learn the latent discriminative semantic features versus the human designed attributes.
Yes, please see the feature. Please see the picture shown in. While the user-defined attributes are fixed and are usually shared between many categories. So if there exists two categories sharing too many attributes, they will be hardly distinguishable. So we should learn the discriminative features. Yes.
Okay, thank you. Let's thank the speaker again.
Excuse me, I have one question. Can I ask one question?
Oh, yes.
So you mentioned that you crop the images and then do bilinear interpolation for zooming in.
Yes.
So my question is, first of all, how do you identify the region in an image, where to crop, and how do you crop that? And second question is, did you experiment without bilinear interpolation and see how the results look?
Okay, first, well, our proposed zoom night is learned with final triplet loss. That is to say, we do not use additional loss functions to train the zoom night, and second, sorry, I do not try to remove the bilinear interpolation to see whether the performance will. Okay, sorry.
It's okay.
Yes.
Okay. This is the end of the oral session. We're going to move to spotlights. Before we move to spotlights, I would like to invite some of the the spotlight presenters are not seated here. So S3 and S5 and S8, are you here? Okay, if you could take the seat corresponding to your spotlight number, that would be great. Okay, so let's start with our spotlight session.
So good morning, everyone. I'm Wei-Chih from UC Merced. Today I'm going to introduce our work, Learning to Adapt Structured Output Space for Semantic Segmentation. This is a joint work with NEC Labs. Our task is cross-domain semantic segmentation. As you may know, collecting annotations for semantic segmentation is quite expensive. To address this issue, there's a recent trend to train a model on a synthetic source domain, as shown on the left, where the annotations are easier to collect because of a render engine. And we want to see whether this synthetic data trained model can generalize well to the real-world data, which is the target domain on the right with no annotation. Unfortunately, in practice, deep neural networks do not generalize well. We show an example here where the target domain is the cityscapes dataset. If we train the model directly on the cityscape dataset, the prediction results are pretty good. However, if we train the model only on the synthetic dataset, for example, GDA5, you can see the results are much worse. This is because the appearance differences, also known as the domain gap, is quite large between the real and synthetic dataset. In the domain annotation problem, we found that Even though the appearance gap between the source and target domain is large, the spatial layout of semantic segmentation is still quite similar between two domains. For example, the bottom part of semantic segmentation will mostly be road, and the pedestrians are mostly on the road, on the sidewalk. Therefore, we propose a method based on the observation that the output space of semantic segmentation is highly structured. So we first introduced the feature space adaptation, which is commonly used in the recent work to tackle the problem of domain adaptation. Given a segmentation network, we pass both the source image and target image through the network. Then the domain adaptation module takes the feature maps from both domains as input. For source domain feature, we can train the network with the source ground truth. Then a discriminator is applied for adversarial learning to make the target feature distribution as close as possible to the source domain feature. However, based on the previous observation, we think why don't we directly apply the adaptation module on the output space? Specifically, to transform the framework from feature adaptation to output space adaptation, what we have to do is to apply the softmax layer on both source and target features. Then we use the soft prediction maps as an input to the discriminator. In this way, the adversarial learning can better align the distribution of the structure output between the two domains. We also find that applying the domain adaptation module on multiple levels can better adapt the lower level feature and improve the performance. We present the quantitative results when adapting from synthetic to real dataset. We first show the method based on BGG16. Our single level model performs better than state-of-the-art methods by 6% IOU. When using the ResNet as a backbone network, applying adversarial learning in the output space instead of feature space brings 2.1 IOU improvement. And applying the proposed method in multi-level brings another 1 point. We also test our method when adapting from cities to cities with different weather conditions. Our method improves the segmentation quality significantly compared to the baseline results. In conclusion, we propose a domain adaptation method for semantic segmentation using adversarial learning in the output space with a multi-level objective function. Our code and models are already available online. So our post ID is D16. So welcome to our poster for more details and discussions. Thank you.
Good morning, everyone. So today I'd like to present our work on multitask learning for scene understanding, and this is joint work with Jianguo and Roberto Cipolla. So when you think of scene understanding, you might think of semantic segmentation or depth estimation, and these tasks might come to mind. But scene understanding is really a multitask learning problem. You need to understand both the semantics and the geometry of the scene. So in this work, we focus on it as a multitask learning problem. Multitask learning is the idea that we try and leverage ideas and information from more than one task to improve the representation, improve in performance, both learning efficiency and performance on each task alone. So we can formulate a basic convolutional architecture to do this. You can see here, so we have a shared encoder followed by a small decoder for each task. Now, one of the important points here is that the majority of the compute is in the encoder and it's shared between each task. That might be something like a ResNet, whereas each decoder is only 1 or 2 layers. So we find that it's really important to weight the losses appropriately when you have multitask learning. All the literature I could find in this area either uniformly weights the losses or does some naive, crude grid search manual tuning. So if you look at this experiment here, what we do is we vary the weight between two tasks in the loss. So on the far left, you can see we're just learning instant segmentation with a weight of 1 and depth estimation with a weight of 0. And on the far right, the converse, we're learning just depth estimation but not instant segmentation. And you can see for some weight in between, there's an optimal weighting which improves the performance of each task compared to the individual tasks on each side. So in this work, we propose a method to learn that weighting because doing it with grid search is really expensive. What we do is we consider task uncertainty. We can learn an uncertainty which is dependent on the task, so not dependent on the input data, but it measures the uncertainty of the task itself. And we use this as a proxy for a weighting for the losses. So the intuition is that the weighting for the loss should depend on things like the magnitude of the output. If you're regressing depth in meters or kilometers, then your weighting should change. Or it should change depending on the difficulty of the task. And uncertainty captures both of these things. And we can formulate this loss with a maximum likelihood objective for both classification, like softmax losses, and regression losses like an L1 or an L2 loss. And we can chain this together for arbitrary number of losses and use this to learn a weighting between these tasks. So to talk about some of our results, what we can do is we can train an individual model on each of these tasks alone, and you can see the baseline numbers are here. Now, to build on this, we could think of some other baselines that, for example, uniformly use weights, which is the fourth line here, or we could approximately tune with grid search the weights. But this is extremely expensive, takes lots of GPUs, and doesn't scale very well when you have lots of tasks. But you can see that uniform tuning of the weights doesn't perform very well. If you approximately tune them, you get a pretty good performance. Now, when you look at our method of weighting the tasks by uncertainty, you can see that when you consider two tasks together, you can improve performance further. And further still, when you learn all three tasks together with uncertainty weighting, you get the best performance. So this shows that we can improve the performance by using this weighting method. So here are some of our qualitative results. So you can see we can learn from an input image in the top left, we can learn semantic segmentation, depth estimation, and instance segmentation in this single model. And you can see the qualitative results are quite smooth, even though this is a per-frame model, so there's no temporal information here. We also noticed some interesting things like the performance in each task is quite correlated. They sort of fail in similar areas, but conversely, they also use each other's information to aid inference. For example, some depth information might be useful to do edge segmentation and to get class boundaries accurately. Thank you very much.
Hi all, I am Yi-Hsuan from Pheng-Ann University in China. In the next 4 minutes, I will briefly introduce our work jointly localized and describing events for dense video questioning. So what do we mean by dense video questioning and what is the difference with traditional video questioning? Take the video as an example. The output sentence generated by traditional video questioning is a man is playing frisbee with a dog, which is unable to describe the procedure of playing frisbee with a dog in detail. In contrast, the task of dense video questioning is to localize all the events occurring in the video and produce a sentence for each event. As such, the difficulty of dense video questioning originates from two aspects. First is how to accurately localize each event in time. Second is how to design a powerful sentence generation model. In our paper, we propose a new architecture to unify the localization of temporal event proposals and sentence generations. Especially, the input video is first encoded into a series of level feature visual 3D CNNs, which are fed into temporal event proposal module to produce candidate proposals. The temporal event proposal module is employed by integrating the event background clarification to predict event proposal, temporal coordinate regression to refine the temporal boundary of each proposal, and the descriptive regression to infer the descriptive complexity of each event into a single shot detection architecture. After ranking the candidate proposals with regard to both event lists and descriptive list scores, the top proposals are in turn injected into sentence generation module. The module leverages both attributes and reinforcement learning-based optimization to enhance questioning. The whole system can be trained through the joint and global optimization of detection and questioning in an end-to-end manner. To evaluate our approach, we conduct the experiments on activity question dataset. The dataset consists of about 20,000 YouTube videos, and for each video, there are 3.35 proposals on average and one ground-truth sentence for each proposal. So in the example video, there are 5 temporal proposals, and every 2 proposals may have overlap. Each proposal is described by one sentence. The table summarizes the performance of different models on activity questions validation sets. Overall, the result across set evaluation metrics with ground-truth proposals and learned proposals consistently indicate that our proposal method achieves superior performance against other state-of-the-art video questioning techniques. In particular, The meter score of our method can achieve 10.33% with Guangzhou proposals, making the relative improvement over the best competitor DCE by 13.33%, which is considered as a significant progress on this benchmark. This figure showcases an example of dense video captioning results generated by different methods and human-annotated Guangzhou sentence. It is easy to see that our method can generate more relevant and descriptive sentence. For example, compared to the phrase production the dog's hair in the sentence generated by LSTM, cutting the cat's cost in our method is more precise to describe the last proposal. Thank you very much.
Good morning, everyone. My name is James Clark, and this work is being done with my student, Sivash Gorji, who unfortunately couldn't be here due to visa issues. So the problem we're looking at is to try and estimate salience in videos. And so here we see a scene, fellow looking around. Not much is happening in the scene, but the fixations and attention actually shifts around quite a bit. It's being pulled by the face of the person and also being pushed by his gaze shifts. And we want to try and model this. And the approach we're going to be using is based on a method we actually introduced last year at CVPR for static saliency, just single images. It's called attentional push. And this is sort of the power of regions to push your attention to certain places rather than to attract certain places. Okay, and in particular, the static attentional push we talked about last year looked at the gaze of scene actors, people in the scene, to push the attention towards what they're looking at. And so what we want to do is try and enhance the static saliency models to allow it to start to estimate these dynamic saliency models. And the reason that we're sticking with basing on static saliency models is that these are fairly good now. They've used these large eye movement databases to allow deep learning methods to do fairly well. Now, these benefits have not been fully realized in dynamic saliency models because we don't have the same large scale data sets for eye movements in dynamic videos. They're coming, but we want to base our thing on static saliency and augment it. And there's a number of challenges when you go to spatial temporal saliency. The usual things, you have more processing required to handle the things, but also we have to worry about long-term temporal correlations. And also, if you think about videos, when you look at a video frame, each video frame is only seen for a short period of time, where if you look at a static image, you can look at this for a long period of time. So it changes the way that humans process these frames. And so the dynamic attentional push, there's some interesting aspects to it. Attentional push seems to be stronger when watching videos because the viewer is more immersed in the scene, so they're more strongly affected by attentional push cues. And so we want to extend the static attentional push we talked about last year into the dynamic setting. We're going to use 3 dynamic attentional push cues, which have been known for a long time by photographers and cinematographers and so forth. And also we're going to capture long-term temporal correlations with recurrent networks such as LSTM. Okay, here we see something interesting. We see a video which looks to be static, but it occurs just after the person moved his gaze to a frying pan. You see the attention sort of starts at the frying pan and moves back to the face over about 1.5 seconds, whereas the static attention would get the same thing in all of these. Now, the 3 dynamic attentional cues we're going to look at are actor gaze shift. So when the actor moves its face, your attention's pushed. We're looking at rapid scene changes such as cuts, and there the attention tends to go towards the center of the screen after the cut. And then finally, we're going to look at bounce of attention. So if you're attending to a person in the scene that moves off of the scene, the attention shifts back to the center. And this is known by filmmakers and so forth. So we're going to integrate these 3 cues using some features with LSTMs in combination with a good static saliency model, whatever your best is. And the results are shown here. We have more results you can see in the poster in the paper. Here we have the same sequence we saw before. On the left, we have the ground truth. We have the shift of attention. In the center, we have static saliency, which doesn't change. And our method sort of mirrors the actual dynamic ground truth attention. Thank you very much.
Good morning, everyone. I'm Wei-Chih from National Lab of Pattern Recognition in Institute of Automation, Chinese Academy of Science. Inspired by recent neural memory models, for example, neural Turing machine, we propose a multimodal memory for video captioning. As we know, the task of video captioning is to automatically generate a natural sentence to describe an input video clip. There are 4 main challenges for video captioning. The first is to learn compact and informative video representation. The second is about how to build a powerful language model. The third is to learn efficient semantic mapping between video and text. The last is to build a proper optimization algorithm to ensure that the training objective is consistent with human evaluation. In this work, we focus on the semantic mapping between video and text by explicitly modeling a shared multimodal memory for video and sentence, which can not only model long-term visual texture dependency, but also guide visual attention to solve multimodal semantic misalignment. Our model consists of 3 components: CN-based video encoder, LSTM-based text decoder, and multimodal memory. CN-based video encoder first extracts video frame or clip features using the pre-trained 2D or 3D CNs. LSTM-based text decoder models the sentence generation with the LSTM-RN architecture. Multimodal memory contains a memory matrix to interact with video and sentence with multiple read and write operations. For the detail of the architecture, first, the LSTM-based text decoder writes previous hidden representation into the multimodal memory to summarize the previous textual information. Second, the updated memory content is read out to get a visual attention model to select prediction-related visual information. Third, the selected visual information where our attention model will be written into the memory for updating. Fourth, the updated memory is read out for the sentence generation, iterating these 4 steps to generate the full sentence. To verify the effectiveness of our model, we perform extensive experiments on MSVD dataset. This dataset is a widely used benchmark for video captioning, which consists of 1,917 video clips and 80,000 sentences. The table shows the performance comparison with the other 10 state-of-the-art methods using single visual feature on this dataset. From the comparison results, we can see that our model performs much better than the other methods in many evaluation metrics. We also compare with the baseline method using different visual features on MSR VTT dataset. Compare with the MSVD, MSR VTT is a recently released benchmark dataset, which has the largest number of video sentence pairs. This table shows comparison results. We can also say that our method consistently outperformed the corresponding baseline methods. This figure illustrates several descriptions generated by our model, the baseline model and the human annotated ground truth on the test set of MSVD. We can see that our model generates more relevant object terms than the baseline model. For example, baseball versus softball in the third video. And our model places more focus on the described targets than the baseline model. Please come to our poster for more details. The poster number is E2. Thanks.
Good morning. I'm Ming-Hsuan from University of Minnesota. In this talk, I'm going to introduce our work on image sentiment and visual attention. This is a joint work with Shaojing Fan, Zhiti Shen, Brian Koenig, Juan Xu, Mohan Kankahali, and Catherine Zhao. Modeling human visual attention is of great importance in many applications, such as human-computer interaction, web page design, social robotics, and neuroscience. Human visual attention is directed by various visual cues, from low-level contrast to high-level semantics. For example, most people involuntarily look at faces when we see a picture like this. In this study, we investigate how different sentimental properties influence where people look in images. In general, emotion-eliciting stimuli such as a happy face or a dangerous snake attract more attention than neutral ones. While computational models of visual attention have been intensively studied, very few have systematically measured the correlation between sentiment and attention. To address this problem, we developed an eye-tracking dataset featuring images with strong emotional properties. Our extensive analysis suggested various prioritization effects of these properties. Considering such effects, we developed a new computational model for predicting visual attention in emotional context. We collected eye fixations from a pool of 16 observers and 1,019 emotion-eliciting images. More than 4,000 objects were segmented and annotated with 33 sentimental attributes. We grouped these attributes into 3 categories: positive, negative, and neutral. We observed that emotional elements attract attention very strongly, especially in social context where human activities and interactions are involved. The density of eye fixations in positive and negative elements are about 30% higher than those in the neutral ones. Emotional elements also attract attention rapidly. Here, the raw meat held in the zookeeper's hand immediately attracts attention, followed by the crocodile's wide-open mouth. Positive and negative elements capture the first eye fixation about twice as many as the neutral ones. So, with a particular emphasis on the relative importance among different visual cues, we propose a deep neural network model for saliency prediction. The architecture follows conventional saliency prediction models with a double-scale convolutional feature extraction and linear integration to combine these features into a saliency map. Instead of directly combining feature maps with static weights, we introduce a context-aware subnetwork to dynamically prioritize these feature maps. Specifically, a fully connected layer computes context-relevant weights of the features based on their spatial and semantic relationship with each other. With the improved feature prioritization, our model achieves the state-of-the-art performances on our new dataset as well as public datasets. It successfully captures the emotional elements in the images and better prioritizes these elements regarding their saliency values and orders. We visualize the learned features by correlating them with the labeled sentiment attributes. These are example image patches producing the highest activation for happiness, sadness, awe, and disgust. Comparison between models with and without context awareness shows improved feature representation of the emotional content. Welcome to our poster for more details and results. Thank you.
Hello, my name is Alexandropoulos, and I'm a staff scientist with IBM. I will be given an overview of a neuromorphic stereo system that we have developed. This is joint work with Hirak Kasyap, Tapan Nayak, Arnon Amir, and Myron Fleckner. In the paper, we introduce an event-based stereo algorithm that can be executed on a spike-based hardware substrate. We use a full graph-based non-von Neumann computation model, which is a way of saying that our algorithm does not use frames, arrays, or any such data structures. We show that this leads to a number of advantages, namely that it can be efficiently mapped on an event-based hardware substrate. We show that on an input from dynamic vision sensors, it can produce up to 2,000 disparity maps per second. Also, in terms of energy consumption, we demonstrate 2 orders of magnitude improvement compared to similar work implemented on a low-power CPU architecture. We also observe up to 11 milliseconds latency. In the next slide, I give an example of the types of outputs that can be produced by a pair of dynamic vision sensors. A dynamic vision sensor emulates in some ways the human retina and provides sparse inputs to our system. The video shown here shows the left and right camera output on a fast-moving fan. Each frame in this video corresponds to 1 millisecond worth of data produced by the stereo sensors. This data is in turn sent to a cluster of neuromorphic chips. Neuromorphic computing is all about energy efficiency, volume efficiency, speed, and scalability. In this case, we use a cluster of 2 North chips. Each chip has 1 million spiky neurons, 256 million synapses, and consumes little power, typically between 73 and 100 milliwatts, depending on the application. The True North neuromorphic chip has been used for high-throughput convolutional neural networks, character recognition, optic flow, saliency, and gesture recognition. So please feel free to pass by the IBM booth to see a live demonstration of a gesture recognition system that we have built and which is running on True North. So from an algorithmic perspective, the main contribution of this paper is the formulation of the stereo problem as a system of equations that can be efficiently mapped to a spiking-based hardware substrate. For obvious reasons, I do not give details on how these equations are defined, so please see the paper for more details. A True North program is simply a system of interacting equations. These equations are defined by a membrane potential that gets updated every tick, as well as by an activation function that outputs a spike whenever a membrane potential threshold is exceeded. We define systems of such interacting equations which efficiently implement a number of important stereo subroutines, such as the ones shown on the left. These include rectification, spatiotemporal scaling, morphological erosion and dilation, Hadamard product-based matching, winner-take-all, and left-right consistency constraints. Thank you very much for your attention.
So hello everyone, I'm Pheng-Ann from the University of Maryland, and today I will present our work with Tang, an image-based virtual try-on network. This is a joint work with Zhu Wu, Zhe Wu, and Rich and Larry Davis. So our task is to virtual try-on using 2D images. So when customers are shopping online, sometimes they want to say, okay, so what will this clothes look like if I try them on? But they don't usually want to go to the fitting room because it's a waste of time. So our work is, given the image of a user and some target clothes, can we naturally render the clothes onto that person so the person know, okay, what will I look like if I try this on? So this is a pretty challenging and very cute application of computer vision. And we argue that there are 3 desired properties in this task. One is when user upload the image and you try it on, the body parts and pose should be preserved, and the clothing should deform naturally. And lastly, the detail of the clothes should be visually visible in the virtual try-on result. So we're facing a lack of data problem in this challenging task, because ideally we want the training data that the same person with the same pose but wearing different clothes. We don't have data like that. We only have the original image and the target clothing items as shown on the left. And the second challenge is we don't have 3D data of clothes and also the body part. Otherwise, we can just deform the 3D information and warp that onto the body. So we propose VTON. It contains 4 steps. First, we propose a clothing agnostic person representation and use that as an input to an encoder-decoder network so we can generate a virtual try-on result. But the results coarse, so we model the deformation of the clothes using a shape context, and finally a refine network to do the refinement. Because we want to keep the information of the wearer, so we use the post estimation method to extract the pose map, and human parser to extract the body shape and face and hair segment of the person that they want virtual try on the result. And this helps us to keep the information of the person. And in an encoder-decoder network, the input will be a person representation together with the target clothing. And you will use a classic encoder-decoder model, and it outputs a coarse result of the virtual try-on result, and also a mask of clothing that tells, okay, which pixel should correspond to the generated clothing. But this result is not very satisfied as shown in these slides, because some details are missing. For example, the text in the first example and the little yellow giraffe on the last example. that is because for the encoder-decoder, it cannot model the geometry change of the cloth, and it has limited generalization property. So we use a refinement network to make the result more realistic. To be specific, using the mask regenerated by the first step and the target clothing mask, we use a shape context matching to get the transformation of the target clothes. And that gives us a warped clothing that correspond to, okay, which regions of the target of the virtual try-on result, what the clothes will look like. And finally, we use the refinement network. So the refinement network takes the warped image, warped clothing image, and the coarse result, pass several convolutional layers, and it will produce a mask. Tell people, okay, which pixel should we choose from the warped image because it contains more details, and which part choose from the coarse result. And you can see here the coarse result in the orange bounding box has less obvious textures than the red bounding box because they are already refined. And you can see, okay, some textures and result are well preserved in our result. Here are more results, so no matter what the pose is, we can generate pretty good result. Okay, and welcome to our poster. Thank you.
Hi everyone, my name is Pheng-Ann. I'm a master student in Huazhong University of Science and Technology. Our paper is called Multi-Rounded Synthetic Testing via Categorization and Region Segmentation. My collaborators are migrant researchers Sohn, Wen, Professor of National University of Sui Chen-Yan, and my advisor, Professor Zhang. Generally speaking, synthesis can be seen as a special form of the general objects. However, computer with the general objects, characteristics of synthetic challenge to be detected. The text in natural image is always multi-rounded and has large variation in aspect ratio. So in this paper, we propose a method to solve these problems. A method based on two motivations. The first one is that corner points can be used to detect synthesis. In theory, a rectangle box can be determined by two corner points and the size, which perpendicular to the line segment made up by the two corner points, no matter what the orientation, the scale, and the aspect ratio of the box are. So if corner points can be detected, many candidate box can be generated. The second motivation is that position-sensitive segmentation can provide the location and the instance information of the text. This information can help us fill out the false alarms in the candidate text box. We propose a rotated position-sensitive RIR polling to scale candidate box. Give a candidate box, we split the candidate box into 4 bins with a 2x2 normal grid. And then we generate the instance segment of candidate box by assembling the segmentation maps. The scores of the box are calculated by average the instance segment regions. As shown, the scoring mechanism can help us fill out the false alarms effectively. This is the whole pipeline of our measure. Give an input image, corner points, and the segmentation maps are generated by corner detection and position-sensitive segmentation. And then we generate the candidate box for sampling and grouping corner points and score the candidate box with the position-sensitive segmentation maps. The box with low scores will be filled out. The backbone of our network is VGG16. We detect corner with DSSD and segment the text regions with FCN. The corner points detection and the position-sensitive segmentation share the same features of the backbone and can be obtained jointly. We evaluate our method on 5 public datasets. State-of-the-art results are achieved on animals datasets. Besides, our models can run at 10.4 FPS with the input size of 512 by 512. Our model handle the oriented syntax and the long text spell. For example, our oriented syntax dataset ICDR 2015, our model achieves the F-measure of 84.3, higher than the best one by 3.3 points. On the long-oriented syntax dataset MSR TD500, the F-measure of our measure is 81.5, also much better than the provided special results. So in this paper, new text detection method based on corner localization and position-sensitive segmentation is proposed. oriented text and non-text can be handled well by our proposed method. State-of-the-art results are achieved on several data size. So welcome to our post 8.10. Thanks for listening.
Good morning, I'm Samana Azadi from UC Berkeley, and I want to introduce our multi-content GAN for few-shot font style transfer as a joint work with Adobe Research. So here our motivation is to have a tool similar to Photoshop Color Dropper but for fonts, where we can take a sample from the font of a printed word like gladiator and generate any arbitrary word like gluten-free with the same style. So we are encountered with the data dropout problem in the font domain, where in the input we are given a subset of the letters, and we want to learn a model in order to generate rest of the letters with the same font style. It requires capturing correlations and similarities between the source letters and the unseen ones. For this purpose, we have collected a dataset of 10K fonts with different variations and styles. And we propose a multi-content GAN model composed of two conditional generative adversarial networks. The first network, called as GlyphNet, is designed for predicting coarse glyph shapes given the few observed letters. Considering the 26 glyphs as different content images following the same style, we have a glyph stack in both the input and output of the generator, where in the input we zero out the channels corresponding to the unseen glyphs. So with this novel glyph stack design, correlation between different glyphs is learned across network channels in order to transfer their style automatically. The second network, called as ornamentation network, is designed for transferring color and ornamentation of the observed letters to the grayscale glyphs generated by the glyph network. Going into more detail for each network, GlyphNet is a conditional GAN with a generator and a discriminator filling in the missing glyphs given the few observed letters. We pre-trained this network on our 10K font dataset, where we have ground truth images for all glyph shapes. After a reshape and grayscale channel repetition, we feed the output of the glyph network to the ornamentation network in order to transfer the color and ornamentation of the observed letters to the unseen letters. So similarly, ornamentation network is a conditional GAN with a generator and a discriminator, where we have ground truth images for only a subset of the letters. In addition to the GAN loss, we apply multiple regularizers on these inputs and outputs in order to penalize deviation of the network predictions from given stylized letters, in addition to penalizing the glyph shapes from their initial predictions and avoiding unwanted artifacts. We train both the ornamentation and glyph networks in an end-to-end manner for each specific font. Here you can see some of our results, where for each font, the first row shows the observed letters given to the network, the second row shows multi-content GAN predictions, and the third row shows ground truth images. Here are some other results from famous animations. Given Frozen, you can generate Frozen yogurt. With the Zootopia style, you can say, "Don't hurry, be happy." And with the Pocahontas font, you will respect the earth. Our code is available online, and please come to our poster for more details. Thank you.
Hi, I'm Elish Lizerman from Facebook and the University of Washington. With my collaborators, Lucia Derry, Hayden Schoen, and Ira Kemal-Mahesh-Lizerman, we built a system called Audio-to-Body Dynamics. We all love listening to music and fascinating by pianists performing complicated pieces. So in this paper, we explore what if we are just given the music, no video? can we create the arms and the fingers that correspond to the music? So we developed a system that gets as an input music and outputs a moving avatar playing the music. The system is based on LSTM, recurrent neural network, that processes audio features and generates predictions of upper body landmarks. The predictions are of fingers and the body as well. These predictions are then used to animate the avatar. We trained the LSTM network on recital videos from YouTube. We trained on about 5 hours of playing. The videos are uncalibrated and in the wild. So they are recorded with various lighting conditions, resolution, performer style, music styles, and tempo. To retrieve the upper body and fingers landmarks, we apply pose estimators such as open pose and mask RCNN on each frame, getting moving data of the key points. Our results show that we can indeed predict musicians' movements which would correspond to the music. Predicted movements include arms, body pose, fingers. Training time is important for what kind of details of the movement we would like to grasp and to produce robust output. To validate our system further, we also trained it on an additional instrument, the violin, since playing the violin is very different than playing the piano. We find that our system can also predict movements for playing the violin. Note the different frequencies of the left hand, the bow, versus the right hand fingers. We mapped the landmarks onto a 3D avatar and developed an iOS app that displays the moving avatar in AR environment, such that the avatar is playing the piece in front of you. Here's an example of a test piece that the network generated. And another example. With the violin avatar, it looks as follows. Note how the neck, the head, and the arms are synced with each other and with the music. For more information, please stop by our poster, E14, and try the AR demo at Facebook booth. Thank you.
Good morning, everyone. I'm Dongyu from Nankai University, and this is a joint work with authors from Cardiff University and UC Merced. So this paper focuses on recognizing sentiment from natural images. And the previous work has proved that sentiments can be evoked from the specific regions that has the discriminative information, while the traditional detection method uses the single bounding box to label object. The sentiment regions are represented with a soft proposal due to the subjectivity. So we propose a weakly supervised framework to utilize such localized information while only requiring the image level labels, which is the simplest and the most efficiency annotation. So this paper proposes a weakly supervised coupled network, namely WSCNet, with 2 branches for visual sentiment analysis. And the basic network makes use of a fully convolutional network to preserve the spatial information. And in the detection branch, we first add the 1x1 convolutional layer to capture multiple information for each sentiment class. And then the proposed cross-spatial pooling strategy is implied to summarize all the information as the image level score, so that the detection branch can be trained with the image level label only. And the detection branch captures the localized representation by coupling the sentiment map with the deep features. And then both the original holistic representation and the localized representation are combined for a more semantic vector. To generate the sentiment map, we combine all the class activation maps with corresponding scores from the softmax layer in the detection branch. As shown in the figure, the maps with high scores are from the related sentiment class. For example, the sadness and anger for the fair image, which can provide the complementary information. And we conduct the experiments on 6 public datasets for sentiment classification task and evaluate the detection task on the emotion ROI dataset, which is the only dataset that provides the detailed region annotation. And our backbone network is ResNet. So we evaluate the proposed WSCNet against different traditional methods, CNN-based methods, the state-of-the-art sentiment classification methods, and other weakly supervised learning methods. And the results show that our proposed WSCNet consistently performs favorably against other methods on all the data sets. And in addition, on the detection task, the WSCNet also performs favorably against other weakly supervised learning methods while achieving comparable performance with the fully supervised detection method. And as can be seen, the object-based weakly supervised method mainly focuses on the foreground objects, while our method can extend the regions to other sentiment-related background. So, welcome to our poster for more details at E16. Thank you.
Okay, hello everyone, I'm Takuma Yagi from the University of Tokyo, and today I would like to talk about my work, future person localization in first-person videos, joint work with Kartikeya Mangalam, Ryo Yonetani, and Yoichitaro. Let me show this video. This video is recorded from a chest-mounted camera, like showing right bottom side. And the man in the middle is walking towards me. And the blue line shows like location history of the person. And what I want to do is to predict the future location of that man, like going to which direction. And let me ask you a question, like, who do you think he'll go to the right? Like, raise your hand. And who do you think he'll go to the left? Thank you. I predicted my probable model predict that like he will go right towards the man, the wearer, and like indeed do so in this example. This is what we achieved in their study. Let me explain the problem formulation. So given our problem is the future person localization, and the input is a 2D location history of a specific person observed in first-person video, and we want to predict the future location of that person in its successive frames. Since this is a prediction problem, we do not have access to the future frames. And the future localization problem itself was already studied in mainly surveillance video or fixed view video, but not in first-person camera scenario. And the challenge is to develop a future person localization method which is tailored to first-person videos. So how to do that? Our approach is to incorporating both target's pose and wearer's ego motion as a silent cue in first-person videos. We've used those cues into a multi-stream convolutional neural network. Our method consists of 3 convolutional streams. Every stream applies 1D convolution, temporal convolution to extract temporal patterns in every modality. And we fuse such 3 cues in a single convolution network and directly predict the 2D location, future locations of a person. To validate the method, we collected a new data set of crowded walking scenes, and it contains 4-point-hour videos of walking crowded scenes. And we applied automated person tracking method, and resulted in 5,000 diverse tracklets in total. Yeah, here's the name. Here we predict 1 second futures from 1 second input, and as you can see, even when the wearer is like trying to move right, our method is able to predict the future location in low prediction error, and like beating the baselines such as social SEM. And quantitatively, our method achieved 1 second prediction error of 6% with respect to the frame width, and this is almost equivalent to 60 centimeter in physical scale, outperforming other baseline methods. And we also conducted an ablation study and confirmed that the pose and ego motion has a complementary effect of boosting the future localization performance. To summarize, we proposed a new problem of future person localization in first-person videos, and we confirmed that the target pose and wearer's ego motion will effectively contribute to boosting future person localization performance. And this will opens a new direction about predicting future person location from a portable first-person camera. For details, please come visit to our poster E18, and I would like to talk with you. Thank you for your attention.
So this concludes the session. Let's thank all our speakers again.